Section 8.3, Power Series Solutions. At this point in Chapter 8, we want to move towards solving second-order differential equations and first-order differential equations also that have variable coefficients, and we haven't done much of that thus far in the course. In order to do that, we need to use methods from power series that you may remember from Calculus 2. And so just to jog that memory a little bit, recall that if you look at a summation from n equals 0 to infinity of a sub n times x minus x naught to the n, then this is called a power series. The a sub n are called the coefficients. X naught is called the center of the power series. And here we have it written in summation form, but we could expand this out and notice that this is an infinite series. It's an infinitely long polynomial. And here the coefficients are a0, a1, a2, a3, and so on. You may recall from your calculus theory that every power series has a radius of convergence. So this is centered at x naught. It has a radius of convergence. The radius of convergence is either 0, a finite number between 0 and infinity, or it can be infinite. And the radius of convergence just told you how far you could go from the center and be guaranteed to get convergence of this series, in the sense that if you pick an x that's in this interval, you plug it into this series, then the numerical series will converge. So a classic example of these kinds of functions or these kinds of series are the Taylor series for a function about x equals x naught. So if you think of this as defining a function f of x, then the coefficients here, if you use the formula for the Taylor coefficient, the nth Taylor coefficient is just the nth derivative of f evaluated at your x naught all over n factorial. These are called the Taylor coefficients, and so this would be a particular type of power series that we have here. And so some famous power series, ones that you should be familiar with from your calculus experience, is if you calculate the Taylor series for the function e to the x about x equals 0, you get this. You calculated in Calculus 2 that it has an infinite radius of convergence via the ratio test. And similarly, sine x has this infinite series form that you can expand out like this. It also has an infinite radius of convergence. Cosine x looks like this, has an infinite radius of convergence. And the famous geometric series has this as its series, and remember it has a radius of convergence of 1. So a concept that we need before we can bring all of this to bear in the context of differential equations is the idea of an ordinary point and a singular point, and that requires us to talk about a function being analytic at a point. So definition, a function f is analytic at x equals x1 if its power series converges on an open interval about x equals x1. In other words, if it has a positive radius of convergence at x equals x1. So for example, f of x equals e to the x is an analytic function at x equals 0, or any x actually, because we already said that it has an infinite radius of convergence. So that means if you pick any x on the interval from minus infinity to infinity, if you were to expand e to the x in a power series there, you're guaranteed that it converges. And all this is requiring is that it has a positive radius of convergence about its center. And so e to the x is an analytic function at x equals 0. On the other hand, f of x equals 1 over 1 minus x is not analytic, say, at x equals 1, because you may remember that the geometric series, it converges if and only if the absolute value of your geometric ratio is less than 1. So if the absolute value of x is less than 1. So it converges in this open interval, but it does not converge here at the endpoints. So this function is analytic in the open interval minus 1 to 1, but it's not analytic at x equals 1 or minus 1 because the series diverges there. So back to differential equations. If we consider a general second-order linear homogeneous differential equation, but this time with not necessarily constant coefficients, so we put functions p of x and q of x here, let's call this equation star, then we want to introduce two more definitions. First, we will say that the point x naught is an ordinary point of our differential equation if the p function and the q function are analytic at x naught. So we just talked about how to check if a function is analytic. So here if we have these at a certain point, so here if we have these functions, we'll say that x naught is an ordinary point if both of these functions are analytic at x naught. If either one fails the test to be analytic, then we call x naught a singular point for the differential equation. So let's look at some examples. Let's suppose we have this differential equation. Now right now it doesn't match our form of star because it has to have a leading coefficient of 1. So we'll divide through by x with the stipulation that x is not 0. And so we get here. And now if we look at this, this is our p function, this is our q function. Let's look at our p of x. Notice this function is undefined at x equals minus 1. And also if you rewrote this as 1 over 1 minus a minus x, it reminds us of a geometric series, the sum of a geometric series. This function is not defined at x equals minus 1. Its power series does not converge at x equals minus 1. So minus 1 would be a singular point for this differential equation. On the other hand, if you took the q function, q of x is sine of x over x, and you were to expand sine x out in its power series and expand and leave x alone, and then you were just to simplify this, notice that this series does converge at x equals 0, even though it looks like that the denominator would be 0 at 0. The power series does converge there. So you just need to be careful to check about the convergence of the power series at a particular point to know if it's a singular point or an ordinary point. Okay? And the reason that this is very important is the techniques that we're going to learn in section 8.3 tell us how to find a power series solution to a differential equation if we're finding it at an ordinary point. The methods that I'm going to show you in this section will not work if our point is a singular point. There are other methods that do work. There are variations on this theme, and they're more complicated. But everything that we're going to show you in this section is predicated on the function being, the point being an ordinary point of the differential equation. So let's find a power series solution about x equals 0 for the first order differential equation y prime plus 2x times y equals 0. So first note that x equals 0 is an ordinary point, because notice my function here, my coefficient function, I have a leading coefficient of 1. So my p function, I don't have a q function here. My p function is 2x. That's polynomial. That is a perfectly analytic function at everywhere, and in particular at 0. So here's how we're going to find power series solutions. We're first going to look for a function, y of x, a solution y of x, of the form, it's going to be an infinite series centered at where they tell us to center this at. So it's going to be an infinite series centered at 0. So this simplifies to this. And if we write this out, we expand it out, it looks like this. So our goal, what does it mean to find a solution in this context? It means finding all of the coefficients. And there's infinitely many coefficients to find. So how are we going to find all of those coefficients? Well, if you just play along with me, we're going to do what we've done all course long. We're going to say, if you're looking for a solution of this form, we're going to plug this back into the differential equation. If it is a bona fide solution, we should get a true statement, and we're going to see what that gives us. So here we're going to calculate the derivative. Remember, your power series theory says that you can differentiate a power series term by term. So here, if I differentiate this, I leave the constant a n alone. I bring the power down. I get nx to the n minus 1. Remember, I'm going to lose the constant term in my series here. So whereas this series started from n equals 0 up to infinity, the derivative series is going to start at 1 because I'm going to lose a term in my series. The derivative of this constant term is just 0. And so we need to start our index at 1. So now we get this in its expanded form. Some people like to work in the expanded form. Some people like to work in the sigma form. I'll mainly work in the sigma form, but we should be comfortable doing either one. If we plug this back into our differential equation, y prime plus 2xy equals 0. I'll plug this in for y prime, highlighted in blue. The 2x is just our coefficient function. I'll leave it alone. And then the form of our solution y of x looks like this in yellow. And now if you stare at this, this is a combination of summations that has to equal 0. And the idea here is I would like to rewrite this as one big summation, but I can't do that right now because notice the sums, there's several different things going on. Number one, they don't have like terms here. This is an x to the n and this is an x to the n minus 1. But they also, their indices don't start at the same places. This starts at 0 and this starts at 1. So in order to rectify the situation, we'll work on these at one at a time. We're going to do what's called shifting the index. And what we're going to do is just make these match up in a way that will be convenient to us. So what we're going to do in order to shift the index is we're just going to try to get a common term on this back end. And so we really don't care if we have these, we want these to be the same, these underlined in blue. We don't care if they were x to the n's, x to the n plus 1, x to the n minus 1, but we want to shift the index so that they're the same. So the idea here is, why don't we say, just to get practice at this, I'm going to make this term on the back end, I'm going to make it an x to the n. And on this term, I'm going to make it an x to the n. Now I can do that, and the way that it works is, if I want to move this index from an n plus 1 down to an n, so I want to bump this down by 1, then that means I have to bump this down by 1, and that means I have to bump this up by 1. And if you just write it out, you'll see that that's the way that this works. If you want to move this down 1, up 1. If I want to move this up 1, because I'm trying to make them both be x to the n, up 1, up 1, up 1, and on the summation it goes in the opposite way, so this has to go down 1. So what's going to happen is shift all of these down 1, shift this guy up 1, shift all of these up 1, and shift this guy down 1. And if you do that, stay with me, if we shift this one down 1, down 1, up 1, up 1, up 1, up 1, down 1. Very important. So we fixed, there's two issues here. We said that these weren't like terms and that the summations didn't start at the same place. We've rectified one of those situations. Notice on the back end, they both have x to the n, so that's forward progress. But now the indices don't match. And when the indices don't match, what I want you to do, one starts later than the other. Notice this one starts earlier, this one starts later. So that means this series is going to have one more term in it than this series in a sense. It starts at n equals 0. And so what we want to do is let's peel off this one starts later. So this is going to dictate what's happening in this example. Let's peel off the n equals 0 term from this, and then we'll get the n equals 0 term plus all the terms from 1 on up to infinity, and that'll force the indices to match. So we'll leave this one alone. We'll peel off the n equals 0 term, and if we do that, the n equals 0 term is a sub 0 plus 1 times 0 plus 1 times x to the 0. So that's just a1 times 1 times x to the 0. That's this. Plus, we've got all the other terms in the series. So summation, it equals 1 to infinity of the same pattern. So this is just another way to write this. But it has the advantage that now what is in the summation starts at 1. This we want to leave alone. It's perfectly fine. Leave it alone. And we still have equals 0 from here. So now stare at this. What we have is in the summation parts, our summations have a common x to the n on the back end. They have a sum, they start at the same place, n equals 1. So we can combine these into one big summation. Just leave this alone. This is just an a1. We will combine this into one big summation, an plus 1 times n plus 1. And we'll go ahead and factor out an x to the n because they have an x to the n common. We'll factor that out on the back end. So we get an an plus 1 times n plus 1 plus a 2a sub n minus 1 all times x to the n. And that still equals 0 because that's the right-hand side of our differential equation. And so now follow me on the logic here. This is just a big infinitely long polynomial. Notice this is the constant term. This is the x to the first power term, x to the second power term, x to the third power term, and so on. And so if this polynomial, this infinitely long polynomial, is going to equal 0, the only way that that can happen is if all of its coefficients are 0. So notice the constant here has to be 0. And here, this is playing the role of the coefficient of the x to the n term. And every one of those coefficients has to be 0. I didn't say that every one of these has to be 0. This thing in brackets has to be equal to 0 because it's the coefficient of the nth term in the series. And the series equals 0. So for free, I get that a1 has to be 0. And then I get that everything in the brackets, the combination of that's in the brackets has to equal 0. And that's true for n equals 1, 2, 3, dot, dot, dot. So notice, this is called a recurrence relation. And so it has a sub n plus 1s in it and a sub n minus 1s. So what I want you to do is solve for the future in terms of the past. So let's solve for this latest term. So we'll throw this to the other side and we'll divide by n plus 1. And so we get that an plus 1 is minus 2 times a sub n minus 1 over n plus 1. And that's true so long as n is equal to 1, 2, dot, dot, dot. This is called a recursion relation for the coefficients because notice it just has a recursion for finding the future coefficients in terms of the past ones. Now in order to get this recursion going, we have to seed this recursion, and we have a seed value here because we know that A1 is 0. So watch what happens. We know that A1 is 0. Let's highlight that. That is known. We need to find the other coefficients. And so what we're going to do is we'll let n be 1 here. If we plug in n equals 1 into this, we get A2. We plug in n equals 1 into this, we get a minus 2A0 over 1 plus 1. So that's what we have here. So that's just minus 2A0 over 2. So that's just minus A0. I don't know A0, so that's the most I can do. I'm just going to stop here. Stop there. Let's plug n equals 2 into this. Well, that's going to give me an A3 equals minus 2A2 over 2 plus 1. That's exactly what I have here. Now that simplifies to minus 2/3 times A1, but hey, I know what A1 is. A1 is 0, so let's put that in. That gives me a 0. So now I know that A3 is 0. Let's plug in n equals 3 into this. Then we could keep doing this all day long. If we plug in n equals 3 in, we get A4 is minus 2A3 over 3 plus 1. That's what we have here. When the dust settles here, we get a minus 1/2 A2, and I know that A2 is negative A0, so I can replace it with a negative A0. So this gives me a 1/2 A0. And I can keep doing this. I can do this for as many of these as we want. Notice what I'm doing is I'm simplifying these coefficients as much as I can based on the information that I know. So I don't know anything about A0, so I can't simplify these things any further. So if we keep doing this indefinitely, we can find all the coefficients. In practical terms, we're not going to write down infinitely many of them. We'll just find enough to establish a pattern, and then we will stop there. So now let's go back. I claim that we've solved the differential equation. We just need to present our work appropriately. So we started with a solution has the form y of x is summation n equals 0 to infinity of a sub n of x to the n. And then we write it out in an expanded form like this. Now let's just substitute in what we know. We don't know anything about A0. We found that A1 was 0. We found that A2 above was negative A0. We found that A3 was 0. We found that A4 was 1/2 A0. We found that A5 was 0, and so on. This plus dot 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 is very, very important. It shows me that you understand that this is an infinite series, so please don't just truncate this and leave this as it's stopping at an x to the 5th, because it would be wrong. It's not a polynomial, it's an infinite series. And so if we cancel these terms that zero out and we look at what's left, everything that's left has a common factor of A0. Why don't we factor that A0 out and we get this? And if you stare at this, we found a one-parameter family of solutions to this first-order differential equation. And that's exactly what our theory from the beginning of the course says, that if we have a first-order differential equation, we should get a one-parameter family of solutions, and that's exactly what happened. Our one parameter in this case was A0, and it kind of naturally fell out of our work. We never were able to find A0, and that's because we weren't supposed to be able to find A0. To get the general solution to a first-order equation, we should have one arbitrary constant, and there's how it shows up. Okay, let's look at a second-order example. Let's find a power series solution about x equals 0 for the equation x squared plus 1 y double prime plus y equals 0. Now to check to make sure that 0 is an ordinary point, we'll go ahead and put this in its standard form. We'll divide by 1. We'll check that our p here, notice p is the coefficient on the y prime. It's not there, it's 0. This is clearly an analytic function. And then if we look at this function, this is an analytic function also. And so this is an ordinary point. X equals 0 is an ordinary point. So we have the green light to go back. Now here's a key thing. We rewrote it in this form to check the ordinary point, singular point, but we don't want to solve it in this fractional form. We prefer to solve it in this form. So we only rewrote it like this to check. So now we'll put to check our singular point, ordinary point pieces. But now we just want to solve using this because it doesn't have fractions in it. So now let's look for a solution of the form of power series centered at 0. We'll take the first derivative. We'll just do it term by term. Remember to bump the index up by 1. We'll take the second derivative, so that's just the derivative of this. Remember, we'll do it term by term. Don't forget you have to bump your index up by 1 because you're losing that constant term every time. Let's go back to our differential equation. I'm going to leave this part alone. The parentheses are very important. I'll substitute in what y double prime is, plus this is what y is, equals 0 because that's what our differential equation said. Now notice, before we can get going doing the shifting the index and making these match, we need to do a little algebra work first. We need to distribute this here. So let's distribute the x squared plus the 1, and then this is just our last term that was already here. So let's push this x squared inside. That's going to bump this power up by 2. Here there's nothing to do. Here there's nothing to do. So now let's, when we get here, let's take inventory. Look at the back end here. This is x to the n. This is x to the n minus 2. This is x to the n. So they don't match. We need them to match. And since these two already match, why don't we leave those alone and only shift this one? And let's shift it to make it an x to the n. And that way all three will match. We'll deal with the indices second. So we want to shift the index on this one. We want to bump it up 2, up 2, up 2, up 2, down 2. So when we shift the index, this stays the same. This stays the same. We shifted it up 2, up 2, up 2, up 2, down 2. And now if you stare at this line, the back end all has x to the n common, so that's nice. But now look at the indices. This one starts at 0, this one starts at 0, this one starts at 2. The one that starts the latest is really ruling the day here. This starts at 2, so that means we need to peel off the n equals 0 and the n equals 1 terms off of this one, and the n equals 0 and n equals 1 term off of this one, and then we'll have 3 series that start at 2. So this just takes some patience. So let's leave this series alone. Let's peel off the n equals 0 term. The n equals 0 term of this, notice, will be a2 times 2 times 1 times x to the 0. That's what's here. Plus, our n equals 1 term would be a3 times 3 times 2 times x to the first. That's what's here. Plus, don't forget, we have all our infinitely other terms. So now we just get the red summation, but now it's starting at 2 because we've peeled off the first 2 terms. Let's go to the last series. Let's peel off this when n is equal to 0. We get a0 times x to the 0. Plus, peel off when n is equal to 1. We get a1 times x to the 1. Plus, we get all these where the summation starts at 2. And all of that equals 0 because the right-hand side of our differential equation is 0. So notice this is a little bit more involved, but the concepts are all the same. So now, look at our summations. They all have an x to the n on the back end, and they all start at n equals 2. So why don't we gather these terms together, gather our sums together, and rewrite it as one big summation. So if you just gather the like terms here, you're going to get an a2 plus an a0. That will be my constant. If you notice that there's one term that has an x in it and another term that has an x in it, why don't we put those together and factor out the x? And then our summation, we're going to get one big super summation. It's a sum from n equals 2. And then what's inside the summation is going to be this plus this plus this with an x to the n factored out of the backside. So make sure you understand where this comes from, and it all equals 0 because the right-hand side of our differential equation was 0. Now stay with me on the logic here. This is an infinitely long polynomial, and it equals 0. The only way that can be true is if the constant term, the conglomeration here that is playing the role of the constant term has to equal 0. The coefficient that is playing the role of the coefficient of the x term has to be 0. And the coefficient, whatever it is that's playing the role of the x to the n coefficient, has to be 0. So notice this whole chunk has to be 0. This chunk has to be 0. And this chunk in brackets has to be 0. So if we write that down, solving for the future in terms of the past, if this equals 0, then I can solve for a2 to get this. If this part equals 0, then I can solve for a3 to get this. Notice I have 2 seeds in my recursion now. And now my recursion is here. So that means the stuff in brackets has to be 0. And it's good for n equals 2 and up. 2, 3, 4, dot, dot, dot. Why don't we solve for the latest term in terms of the past? So n plus 2 is the latest. So let's throw this to the other side, throw this to the other side, and let's divide by this. We get this, and we need to know where our recursion is good. So this is our recursion relation. These are our 2 seeds. Let's just start with plugging in n equals 2 into here. If we plug n equals 2 into this, we get a4 equals minus a2 times 2 times 1 plus 1 all over 4 times 3. That's what we have here. And so this just gives me a minus 3 over 12 a2. That's a minus 1/4 times a2, but I know that a2 is minus 1/2 a0. So I'll put that in for a2, and when it's all said and done, I get that a4 is 1/8 a0. I don't know anything about A0. That's the best I can do, so I leave it like this. Let's go back to this. Let's plug in n equals 3. We get an A5 equals minus A3 times 3 times 2 plus 1 all over 5 times 4. So this gives us a minus 7 over 20 A3. But hold on, I know A3 is negative 1/6 A1, so I'll plug that in for A3, and that gives me 7 over 120 times A1. That'll give me the value for A5. We'll do one more. We'll do two more actually. If I plug in an n equals 4 into this, I get A6 equals minus A4 times this. And then I simplify this. I plug in what I know about A4. Remember, I've already found A4. A4 is 1/8 A0. So I plug that in, and I simplify, and I get A6 in terms of A0. I do it one more time. When I plug a 5 into this, I get this. This gives me this fraction in terms of A5, which simplifies to, since I know that A5 is 7 over 120 A1, I can simplify this. And I could keep doing this all day long. So notice, in contrast to the last example, when I did as much simplification as I could, I was getting coefficients that are in terms of A0 or A1, and I don't know anything about A0 or A1, and that's going to be okay. So now our solution is, if we do what we did last time, our solution is we're just going to take y of x as our power series template that we had before. If we write it out in its expanded form, don't forget the plus dot dot dot. What we said is I don't know anything about A0, I don't know anything about A1. I'll write in what I know about A2. A2 was minus 1/2 A0, still times x squared. A3 is minus 1/6 A1, still times x3. A4 was 1/8 A0, still times x4. A5 was 7 over 120 times A1 times x to the 5th, and so on. And now if you stare at this, this is a 2-parameter family of solutions. This is exactly how it should have, the story should have ended in a second-order equation. So what we're going to do is let's segregate this into all the terms that have a common A0 and factor it out. This is what you get. And all the terms that have a common A1, let's factor it out, and this is what you get. This is now a 2-parameter family of solutions. Each one of these is an infinite series, is a power series. And so instead of getting y of x as c1 y1 plus c2 y2, we actually did get that. Except instead of getting a C1 and a C2, we got an A0 and an A1, same concept. And instead of getting a Y1 and a Y2, we got an infinite series for Y1 and an infinite series for Y2. So this is totally consistent with everything that we've done throughout the course. Okay, so the last thing we need to handle in preparation for the homework is what if you had initial conditions? So let's take the same differential equation, and suppose I gave you 2 initial conditions as well. Well, our consistent philosophy with initial value problems has been go find the general solution to the differential equation, and you know in this case it should be a 2-parameter family. Evaluate the first initial condition, evaluate the second initial condition. That should give you enough information to solve the 2 constants. So let's stick with that philosophy. We already found above that the general solution looked like this. And then when we apply our first initial condition, I'm just going to evaluate y at 0. Well, if I evaluate y at 0, there's a whole bunch of x's here. And so everywhere I see an x, I put a 0. Everything in this is going to 0 out. Everything in this is going to 0 out except this. And so I'm just going to get a big A0. And this tells me the A0 has to be 1. On the other hand, to apply the second initial condition, I need to take the derivative and then evaluate it at 0. But recall from your calculus theory that a power series can be differentiated term by term. So I could just take the derivative term by term of this. So take the derivative of each term, that's what I've done here. Take the derivative of each term, that's what I've done here. Evaluate this at x equals 0. Notice all of these 0 out. Evaluate all of these at x equals 0. All of these 0 out except for this 1. And so we get that A0 times 0 plus A1 times 1 is 2. That forces A1 to be 2. So just to put a bow on this, we'll return to our general solution, and we'll plug in the values we found for A1, A0, and A1, and this would be the double infinite series, or 2 infinite series. There's one here and one here. This would be the 2 infinite series put together to form a solution to our initial value problem.